Okay, there is the singular value decomposition. A, B, and M by N matrix, rank R. Then we can split A as U sigma V transpose. Okay. Order of A is this is M by N. And what about U? U is an M by N matrix. U is a square matrix, M by N matrix. Sigma is again M by N. Order of sigma and A are same. It is M by N. It is also M by N. Okay. And what about B? B is an N by N matrix. Okay. Then how to construct this U sigma A, U sigma V from A? First we have to find eigen values, then the singular values. Okay. So first we have to find the eigen values lambda 1, lambda 2, etc., lambda n of A transpose A. Okay. Since A has order m by n, A transpose, the order of A transpose is n by m. Okay, so n by m into m by n. So ultimately its order is n by n. So it has n eigenvalues. Okay. Corresponding to this n eigenvalues, we can define its singular values. We know that singular values are the positive square root of eigenvalues. These eigenvalues are not negative. Okay, so we have sigma 1, sigma 2, etc., sigma r plus 1, etc., sigma n. There are n singular values in descending order. Okay, and we suppose we assume that there are only r non-zero singular values. Okay, that is the significance of this R. If rank of the matrix A is R, then it has only R non-zero singular values, or R non-zero eigenvalues are there for A transpose A. Okay, then corresponding to this R non-zero singular values, first we construct a matrix D. D is a square matrix. D is a square matrix, it's a diagonal matrix. Its diagonal entries are precisely the singular values in descending order. Okay, so this is a diagonal matrix. Okay, rest of the elements are 0 by adding sufficient number of 0 such a way that the sigma should be m by n. M by n is the order of A. Clear? So now sigma is clear. Then how to construct V? The construction of V is also easy, because how to construct V? To construct V, V is nothing. V is the matrix V1, V2, etc. V1 is the column, V2 is the second column, etc. Vn is the nth column. And what about V1? They are the orthonormal eigenvectors of A transpose A. Already we have seen how to find the orthonormal eigenvectors of A transpose A. Okay, first you find the eigenvectors, then normalize it. Okay, so this v1, v2, vn are the orthonormal eigenvectors of A transpose A, and order of A transpose A is n by n. So each vector has order n. Okay, so V is an n by n matrix. Clear? So v1, v2, vn's are the orthonormal eigenvectors of A transpose A. Correspond to eigenvalues lambda 1 to etc. lambda. They are in descending order. Okay. The next one, construction of U. How to construct U? Corresponding to this R non-zero singular values, we can define U1, U2 up to UR. Clear? We can define U1, U2 up to UR. They are corresponding to these non-zero singular values. Okay, how to define U1? U1 is defined like this. U1 is A V1 by sigma 1. Okay, what about sigma 1? Actually, sigma 1 is nothing. Sigma 1 is the norm of AV1. You remember it? Okay, so actually the sigma 1 is nothing. Sigma 1 is norm of AV1. Okay, we have seen that in, I think, in previous slide. Yeah, this is remark. The singular values of A are the norm of vectors AV1, AV2, etc. So what is sigma 1? Sigma 1 is the norm of AV1. Okay, similarly sigma 2 is the norm of AV2. Okay, so what about these So what about this one? Actually, this sigma 1 is the norm of AV1. So this is a unit vector. So V1 is unit vector, because sigma 1 is the norm of the numerator. So this is a unit vector. That is a process of normalization. Okay. Anyway, we define U1 and U2 etc. UR. UR is AVR by sigma R. So these vectors are defined only for corresponding to the non-zero eigenvalues or non-zero singular values. Okay. Our aim is to create an m by n matrix. Okay. Our aim is to construct a matrix like this. U is equal to U1, U2 etc. UR plus 1 etc. up to UM. Okay, we have to construct an m by m matrix. The order of each UI is m. Okay, why it is order m? Because A is an m by n matrix and all the VIs are n by 1 matrix. So what is the order of AVI? The order of AVI is m by 1. You got it? So this is m by 1 matrix. So each AVI is m by 1. Okay, so order of each UI is m. There is a column containing m entries. Okay, so for this U there are m rows and we have to construct m columns, U1, U2 up to UM. That's why this is m by m matrix. Okay, then how to construct this extra UIs if needed. Sometimes this R itself m. In some problems R may be m. So we don't need to construct new UIs. If R is less than m, we have to introduce extra m minus R vectors in such a way that the new set is an orthonormal basis of R. Clear? Sometimes this R may be equal to m. So in that context, we don't need to introduce extra vectors. If R is less than m, we have to introduce extra vectors such a way that the new set U1, U2 etc. UM is an orthonormal basis for Rm. That's why write like this, where U1, U2 etc. UM is an extended orthonormal basis from this U1, U2 UR. Okay, so this is the procedure. Then we discussed a problem. Find the singular values of this matrix. Already we know that these are the singular values and they are the corresponding orthonormal eigenvectors. So this is V1, this is V2 and this is V3. Okay, then how to construct sigma? What is sigma? Sigma is defined like this: D and rest of them 0. And what is the order of sigma? What is the order of sigma? Hello. What is the order of sigma?
M by n.
M by n. Here, what is our m and n? Here, it is a 2 by 3 matrix. Correct. So, sigma should be 2 by 3. You got it? Because the sigma and given matrix in same order. Okay. So, sigma should be 2 by 3. So, what about D? What is D? D is a square matrix with the non-zero singular values in descending order. So, what is the first entry of D? What is the first entry?
Sigma 1 6 root 10.
Yeah, that is 6 root 10. And second one?
3 root 10.
3 root 10. Because this matrix has only two non-zero sigmas. The third sigma is 0. Okay, so D contains only non-zero sigmas. So sigma 1, sigma 2 is enough. So what is the value of R? So what is the value of R in this problem? That is 2. 2. That is the rank of this matrix, or that is the number of non-zero eigenvalues. That is the number of non-zero singular values, whatever be, all are same. So anyway, D is this one, 0, 0. Then how to construct sigma? Sigma should of the form D and remaining are 0 and order of sigma should be 2 by 3. So in this case, what about D? This is 6 root 10, 0, 0, 3 root 10, and order should be 2 by 3. So what is our sigma? How to complete sigma? By adding extra row or extra column?
Extra column.
Extra column, they are 0. Now this matrix is 2 by 3 and which is of the form D000. Okay, no need to add extra row because we have to find a sigma such it should be the order of given matrix 2 by 3. So this is sigma. So sigma is okay. Then next one V. V is also very trivial. We know that the matrix V is nothing, the V1, V2, V3. So in this case, our V is equal to 1 by 3, 2 by 3, 2 by 3, minus 2 by 3, by 3, plus 2 by 3, by 3. Yes. This is the matrix V. It is n by n. Okay. Here n is 3. M by n. Here n is 3. V should be 3 by 3 matrix. Okay. Now V and sigma are ready. Next we have to construct U. Okay. How to construct U? What is the procedure? First we have to find the vector U1, U2 corresponding to non-zero singular values. Here we have only two non-zero singular values, sigma 1 and sigma 2. So corresponding to sigma 1 we define U1, corresponding to sigma 2 U2. Okay, so what is U1? What is the definition of U1? What is the definition of U1?
1 by sigma 1.
Not 1 by sigma 1. 1 by sigma 1 times what?
A1.
AV1. Yes. So 1 by sigma times AV1. This is the definition of U1. Okay. Similarly, we can define U2. Okay. So here U1 is equal to 1 by 6 root 10 into A times V1. Now, detail. So A is 4, 11, 14, 8, 7, minus 2. 8 times V1. What is our V1? 1 by 3, 2 by 3, 2 by 3. Okay. Upon simplification, this becomes like this. 3 by root 10 and 1 by root 10. Okay. Similarly, we can construct U2. Okay. U2 is nothing. 1 by sigma 2 times AV2. Upon simplification, this becomes like this, 1 by root 10 and minus 3 by root 10. Okay, now we have two UIs, U1 and U2. Okay, then what is our aim? Our aim is to construct an M by M matrix from UIs. What is the value of M? What is the value of M?
2.
Yeah, M is 2. So we have to construct a 2 by 2 matrix. So what is U? Now U is clear. So what is U? What is U? What about U? What is the first column of U?
U1,
U1, U2. Okay, so our aim is to construct a 2 by 2 matrix. What about this U? Is it 2 by 2? Is this matrix is 2 by 2?
yes.
Yes, this is a 2 by 2 matrix. So no need to add extra vectors such a way that using the extension of basis. Okay, because here R equal to M. You got it? Here R equal to M. We know that R is also 2 and M is also 2. So they are already equal. So we don't need to introduce extra vectors to complete an m by m matrix. Okay. So in this problem, u is u1, u2. So what about u? So this u equal. So this u equal to u1. u1 is 3 by root 10 and 1 by root 10, and u2 is equal to 1 by root 10 and minus 3 by root 10. Okay, now everything is ready. So this is the singular value decomposition of this matrix A. So ultimately you can write this A as, so how, so this means you can write A as like this. This means you can write that A is equal to U sigma V transpose. Okay, this is our U and this is our sigma. This is our V. You substitute here V transpose. Then A sigma V transpose gives, U sigma V transpose gives A. You can verify it. Okay, this is the idea of singular value decomposition. Clear? ഇതിനകത്ത് അത്ര കോംപ്ലിക്കേഷൻ വരണില്ല. ഓക്കെ, ഇവിടെ നമുക്ക് എക്സ്ട്രാ വേണ്ട. വേറൊരു പ്രോബ്ലം നിങ്ങൾക്ക് ഒരു ഔട്ട്ലൈൻ തരാം നിങ്ങൾക്ക്. Suppose you consider another problem. Not this one. Consider another problem, second one. Find the singular value decomposition of A is equal to 1 minus 1 minus 2 2 2 minus 2. Okay, suppose this is the problem. A is equal to 1 minus 1 minus 2 2 2 minus 2. Okay, so we have to find A transpose A. So here A transpose A equal to 9 minus 9 minus 9 9. So its eigenvalues are 18 and 0. Okay, sorry, this is 0. 18 and 0. Okay, so and the corresponding orthonormal, the orthonormal eigenvectors are v1 is equal to 1 by root 2 minus 1 by root 2 and v2 is equal to 1 by root 2 and 1 by root 2. Okay, so A is given, A transpose A equal to this one. Then we have to find eigenvalues and orthonormal eigenvectors. They are orthonormal eigenvectors. Okay, if you find the eigenvectors, then normalize it. So these are v1 and v2. Then then what is our sigma? What about sigma 1 and sigma 2? They are the
Root of 18 and 0.
Yeah, this is root 18 and 0. Okay, so your sigma 1 is root 18 and sigma 2 equal to 0. So order of this matrix A is 3 by 2. Okay, so how to construct? So what is D? What is D? What is the order of D? At least what is the order of D?
Three by 2.
No, my question, what is the order of D, that diagonal matrix? If you to construct sigma, we know that sigma is of the form D and so many zeros, and D should be diagonal. And what are the diagonal entries of sigma? In general, what are the diagonal entries of not sigma? What are the diagonal entries of D?
Root 18 matram.
Yeah, only root 18. Yes, because diagonal entries of D contains only non-zero singular values. We have only one non-zero singular value, is root 18. Okay, this is nothing, this is 3 root 2. Okay, so only one non-zero value. So D is a 1 by 1 matrix like 3 root 2. Okay, then how to construct sigma? or what is sigma? Sigma പറഞ്ഞാലും മതി. What is the first row, second row, third row? ഒന്ന് പറയാമോ? What is the first row of sigma, second row of sigma, and third row of sigma? Sigma should be 3 by 2. So what is the first row?
3 root 2 0.
Then
0 0 0 0.
so this is our sigma. It's a 3 by 2 matrix, and the D is there. Say 1 by n diagonal matrix with containing non-zero singular value. That's all. So sigma is ready. Then V is already ready because we know that V is nothing. V is equal to V1 V2. So V is already ready. No problem. Then next we have to construct our U. Okay, how to construct U? To construct U, what about U1? What about U1? What is U1? Definition. What is U1?
Sigma 1. A V1 by sigma 1.
Yeah, AV1 by sigma 1. U1 is nothing, AV1 by sigma 1. Okay, in this case, AV1 A is this one, V1 is this one. You consider AV1 divided by sigma 1. Sigma 1 is 3 root 2. After simplification, we get like this: 1 by 3 minus 2 by 3, 2 by 3. This vector should be a unit vector because we know that sigma 1 is norm of AV1. So this is a unit vector. U1 is a unit vector. Okay. So we have only one U1 because these UIs are defined corresponding to non-zero singular values. We have only one non-zero singular value. So we have only one U1. Okay. Then what is the size of U? What is the order of U? What will be the order of U?
3 by 3.
Yeah, or U should be M by M. In this case, M is 3. Okay, V is 2. V is N by N. Here, M is 3, N is 2. Our capital V should be 2 by 2. This is N by N. But U is M by M. So it is 3 by 3. Okay, so we have only one U1. Okay, we have only one U1. So we have to introduce 2 more UIs. You got it? So we have to introduce 2 more UIs. Okay. So U should be like this: U1, U2, U3. Then only it is 3 by 3. Okay. And what about this U2 and U3? How to construct this U2 and U3? That is the U2. How to construct U2 and U3? The procedure is this one. The set U1, U2, U3 is orthonormal basis for R3. In general, RM. Here M is 3, so R3. So we have to construct an orthonormal basis from U1. By extending U1, we have to find an orthonormal basis for R3. Okay, how to find orthonormal basis for R3? Normality is easy. By taking a normalization process, we can easily find the normal vectors. But how to find orthogonal vectors? That means what? A set is orthonormal means, first of all, they are mutually orthogonal and all the vectors are unit. Okay, already U1 qualified all the conditions. U1 is normal vector. Okay, then how to construct U2 and U3? What is the property of U2 and U3? U2 should perpendicular to U1 and U3 also perpendicular to U1. You got it? Because it is an orthonormal. All the vectors are mutually perpendicular. Okay, so that means what? That means we have to construct, suppose that means we have to construct a vector X. Suppose we have to construct a vector X, let it be like this: x1, x2, x3. So we have to construct 2 vectors x1, x2, x3 such a way that they are orthogonal to U1. Okay, orthogonal to U1 means the inner product of U1 x equal to 0. You got it? Inner product of U1 x equal to 0. What is inner product of U1 x? Suppose x is equal to x1, x2, x3. Then what is inner product of U1 x? Suppose x is equal to x1, x2, x3. Then what is inner product of U1 x? Suppose x is equal to x1, x2, x3. Then what is inner product of U1 x? Suppose x is equal to x1, x2, x3. Then what is inner product of U1 x? Suppose x is equal to x1, x2, x3. Then what is inner product of U1 x? u1 is here. This is our u1. What is the definition of inner product? Our usual Cartesian inner product, Euclidean inner product. Suppose this is our x, this is our u1. Then how to find the inner product between two vectors?
U transpose X.
Yeah, what is u transpose x? u1 transpose x.
X1 by 3.
Yeah, so this is nothing u1 transpose x, that is equal to x1 by 3 plus minus, sorry, this is minus 2x2 by 3 plus 2x3 by 3 equal to 0. Okay, now 3 is common. Now this 3 is common. So what happened? This become x1 minus 2x2 plus 2x3 equal to 0. You got it? So this u2 and u3 are orthogonal to u1 means we have to find two vectors of the form x1, x2, x3 such a way that x1, x2, x3 satisfies this equation. You got it? Because this vector is orthogonal to u1 means this vector x satisfies this equation. This equation means u1 transpose x is equal to 0. u1 transpose x is like this. So upon simplification we get x1 minus 2x2 plus 2x3 equal to 0. Okay, we can easily solve this equation because we have only one equation and three independent variables. So how many variables are arbitrary? How many variables are arbitrary? What is the rank of the system? What is the rank of this system?
1.
Yeah, 1. What about the number of variables?
3.
3. So 3 minus 1 should be arbitrary. Okay, we can substitute 2 arbitrary. Okay, by substituting 2 arbitrary, we get a collection of solutions. So, this is already okay. About substituting, okay. So suppose we choose x2 and x3 are arbitrary. Suppose we choose x2 and x3 are arbitrary, then that means if we choose x2 is equal to some a and x3 equal to b, we are choosing x2 and x3 are arbitrary. Then what about x1? X1 is equal to x1 is equal to 2a minus 2b. Okay, so our vectors are like this, 2a minus 2b, a, b. These are those vectors satisfying this condition. That means those vectors which are orthogonal to u1. Okay, then what is our aim? Our aim is to find a particular u2 and u3 such a way that this is a basis. This is a orthonormal basis. So it is a basis. It is a basis means it should be linearly independent. Okay, so we have to construct u2 and u3 such a way that the entire set is linearly independent. Okay, how to construct two linearly independent vectors from this collection? It's a very easy technique. How to construct, or what are the two linearly independent vectors from this collection? What is the procedure? And we are arbitrary. How to find two independent vectors from this collection? Okay, suppose we choose a equal to 1 and b equal to 0, then we get one vector like this. When a equal to 1 and b equal to 0, this become 2, 1, 0. Okay, and let it be w1. And we construct another vector which is linearly independent to w1. So we take another combination like this, a equal to 0 and b equal to 1. This is a normal practice. So when a equal to 0 and b equal to 1, we get another vector with a guarantee that that is linearly independent. What about that vector? That is minus 2, 0, 1. Okay, you can easily verify that these two vectors are linearly independent. Okay, anyway, now we have two linearly independent vectors such that this collection is this collection, which collection? The collection u1 w1 w2 is a basis for R3. Is it enough? No, we have to construct an orthonormal basis. Now it is a basis and u1 is orthonormal, u1 is normal because its norm is 1. Okay, so we have to normalize this set. Clear? We have to construct an orthonormal set from this w1 and w2, and we know that this w1 and w2 are linearly independent. How to construct an orthonormal set from a linearly independent set? How to construct an orthonormal set from a linearly independent set? Now we know that this is linearly independent. What is the procedure? What is the name of the procedure? Now we know that this set is linearly independent. You got it? Now we know that this is linearly independent. You can easily verify this is a linearly independent set. Then how to construct orthonormal set from an independent set? Another പേരുണ്ടല്ലോ, നമ്മുടെ Gram-Schmidt process. Using the Gram-Schmidt orthonormal process, we can construct the corresponding orthonormal set from a given linearly independent set. Okay, so using Gram-Schmidt orthonormalization process, we can find the corresponding orthonormal set. But u1 remains same because u1 is already unit, so there is no change for u1. But this w1 become u2 and w1 become u2 and w2 become u3 using Gram-Schmidt orthonormalization process. This is the general problem. This is an example of a general problem. Then after this simplification, after Gram-Schmidt orthonormalization process, we get u2 as like this. u2 is like this: 2 by root 5, 1 by root 5 and 0, and u3 is like this: minus 2 by root 45 and 4 by root 45 and 5 by. Now the problem is solved. In the procedure clear and we have to construct a 3 by 3 u. We have only one u1, so we have to construct extra 2 vectors such a way that the entire set is orthonormal basis. So first we are going to construct a basis. Okay, how to construct a basis? An orthogonal basis. This is not a normal basis, this is an orthogonal basis. How to construct this orthogonal basis? We know that a new vector x should satisfy the condition u1x equal to 0. Okay, u1x means this is equal to 0. By solving this equation, we get x like this. These are the all possible x's satisfying this condition. Out of these collection, we have to pick 2 vectors. Such a way that the new set is a basis. Okay, so for finding 2 linearly independent sets, we choose a equal to 1, b equal to 0, that give a vector. Another vector is given by a equal to 0 and b equal to 1. So it is clear that they are linearly independent. Okay, so we get a new set u1, w1, w2, which is a basis for R2. Okay, then we have to construct an orthonormal basis. Already we know that they are linearly independent. So how to construct the orthonormal basis? That is using Gram-Schmidt orthonormalization process. By applying the Gram-Schmidt orthonormalization process of this u1, w1, w2, we get u1 remains u1 because u1 is already unit, because u1 is a v1 by sigma 1. Sigma 1 is nothing, that is norm of a v1. So that's why this is unit. So there is no change in u1, and w1 become u2 and w3 become u3. And this is the these are the vectors u1, u2, u3. So using this u1, u2, u3, you can write u. Okay, so this is the procedure. ഇതാണ് ഒരു ജനറൽ കേസ്. നിങ്ങളൊന്ന് ചെയ്ത് നോക്കണം കേട്ടോ. ഈ പറഞ്ഞ പ്രൊസീജിയർ എല്ലാം നിങ്ങൾ ചെയ്ത് നോക്കാം, എന്നാലും നിങ്ങൾ പഠിക്കത്തുള്ളൂ. പിന്നെ അത് മേജറായിട്ട് നിങ്ങൾക്ക് 2 കർവുകളാണ് വരുന്നത്. ഒന്ന്, ഫസ്റ്റ് വി ഹാവ് ടു ഫൈൻഡ് v1 and v2 means first we have to find the eigenvectors then we have to normalize it. That's complicated alla, just find the eigenvectors, then just divide with its norm, then we get a normalized eigenvectors. അപ്പോൾ അത് കിട്ടിക്കഴിഞ്ഞാൽ you can write v and sigma. Then ഇതാണ് അടുത്തൊരു മേജർ കർവ് വരുന്നത്, how to construct u. If rank is equal to m, there is no more confusion, because you can directly find all the ui's. You can directly find all the ui's from av1, av2, av3, etc. If rank is less than m, then we have to introduce extra vectors, that using the concept of orthonormal basis of R. അങ്ങനെ വരുമ്പോഴാണ് എക്സ്ട്രാ എഫേർട്ട് വരുന്നത്. ഓക്കെ, ഇതുവരെ ക്ലിയർ ആണെങ്കിൽ നമുക്കിത് സ്റ്റോപ്പ് ചെയ്യാം. ഇതോടുകൂടി ഈ സെഷൻ കഴിയും. യു വിൽ ഗോ ടു നെക്സ്റ്റ് മോഡ്യൂൾ. നമ്മൾ അടുത്ത മോഡ്യൂളിലേക്ക് പോകാൻ പോകണം. എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ ചോദിക്കാം.